Tonight, we're going to explore one of the most fascinating what-if scenarios in all of astrophysics. Imagine two objects, each one almost a star but not quite. They had the mass, they had the ingredients, but they just couldn't cross the finish line. They're called brown dwarfs, and they're the universe's most famous failures. But here's where it gets interesting. What happens if two of these failed stars are locked in a tight orbit, spiraling closer and closer over millions of years until they finally collide? Could two objects that individually failed to become stars somehow succeed together? Could their combined mass ignite the nuclear furnace that neither could light alone? The answer isn't what you'd expect, and the physics behind it will fundamentally change how you think about what it really takes to become a star. Before we go any further, if you enjoy these kinds of deep explorations of the universe, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something fundamental. What makes a star a star? It seems like a simple question, and most people think they already know the answer. Stars are bright, they're hot, they're massive balls of gas hanging in space. All of that is true, but those are just descriptions of what a star looks like from the outside. The real answer, the one that matters for everything we're about to explore, lies deep inside. What truly makes a star is what's happening at its core. A real star is an object where the pressure and temperature at the center have become so extreme that hydrogen atoms are being crushed together, fused into helium, and releasing enormous amounts of energy in the process. That process is called nuclear fusion, and it is the single defining feature that separates a star from everything else in the universe. No sustained hydrogen fusion, no star. It's that clean. It's that absolute. That one threshold divides the objects that shine for billions of years from the ones that slowly cool and fade into darkness. Our sun is the most familiar example. Every single second, deep in the sun's core, roughly 600 million tons of hydrogen are fused into helium. The temperature down there reaches about 27 million degrees Fahrenheit. The pressure is around 265 billion times the atmospheric pressure on Earth's surface. Under those crushing conditions, hydrogen nuclei that would normally repel each other are forced so close together that the strong nuclear force, one of the four fundamental forces of nature, takes over and binds them. What comes out of each reaction is helium, plus a tiny amount of mass converted directly into pure energy. That energy works its way outward through the sun's layers over thousands of years, eventually reaching the surface and radiating into space as the light and heat that makes life on our planet possible. But here's the thing most people never stop to consider. The sun didn't choose to become a star. It didn't decide to start fusing hydrogen one day. It became a star because it had enough mass. That's the single most important factor. If a collapsing ball of gas accumulates enough material, gravity will squeeze its core to the temperatures and pressures needed for hydrogen fusion, and it becomes a star. If it falls short, if it gathers almost enough mass, but not quite, something very different happens. The object tries to become a star and fails. It gets close, maybe heartbreakingly close, but it can't cross the finish line. That object is called a brown dwarf, and tonight we're going to find out what happens when two of them collide. But to understand why a brown dwarf merger is so fascinating, you first need to understand how stars and brown dwarfs are born. Because the story of every star and every failed star begins in exactly the same way. It starts with a cloud. Scattered throughout every galaxy, including our Milky Way, there are enormous clouds of gas and dust called molecular clouds. These clouds are made mostly of hydrogen, the simplest and most abundant element in the universe, mixed with helium and traces of heavier elements. They're cold, typically only about 10 to 20 degrees above absolute zero, and they are vast. A single molecular cloud can stretch across dozens of light years and contain enough raw material to form thousands of stars. Some of the largest, called giant molecular clouds, span hundreds of light years and hold enough gas to produce millions of stars. They are among the biggest individual structures inside a galaxy, and yet most people have never heard of them. Most of the time, these clouds just sit there, held in a delicate balance. The outward push of gas pressure and magnetic fields resists gravity's inward pull, but sometimes something disturbs that balance. A nearby star might explode as a supernova, sending a shockwave rippling through the cloud. Two clouds might drift together and collide. A cloud might simply become dense enough in one region that gravity starts winning the tug of war against pressure. Whatever the trigger, once a patch of the cloud begins to collapse, gravity takes over and the process becomes a runaway. As the material falls inward, it speeds up. Conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in, causes the collapsing gas to rotate faster and flatten into a spinning disc. At the center of this disc, material piles up, growing denser and hotter with each passing moment. This hot, dense knot of compressed gas at the center is called a protostar. It isn't a star yet. It hasn't started fusing hydrogen, but it's on its way. If enough material continues to rain down onto the protostar from the surrounding disk, if its mass keeps growing, then the core temperature will eventually climb high enough for hydrogen fusion to ignite. And at that point, the protostar crosses the threshold. It becomes a true star. For an object like our Sun, this entire journey from a first collapse to stable hydrogen-burning star takes roughly 50 million years. For smaller objects near the hydrogen-burning limit, the contraction phase can stretch even longer because there's less gravitational energy available to power the heating. And here's the crucial detail. A single collapsing cloud doesn't always produce just one protostar. Molecular clouds are enormous, and the collapse process is messy, chaotic, driven by turbulence and competing gravitational pulls. The cloud often fragments into many smaller clumps, each one collapsing independently. Some of those clumps gather enough mass to become true stars, others don't. A single cloud might simultaneously produce massive hot blue stars, modest sun-like stars, tiny red dwarfs, and inevitably, some objects that fall just below the fusion threshold. The cloud doesn't sort its children neatly. It doesn't decide in advance which fragments will succeed and which will fail. That outcome is determined later by how much mass each fragment manages to accumulate before the surrounding gas is blown away or used up. But not every collapsing fragment has enough material to make a star. Some clumps are smaller, they collapse, they heat up, they contract, but they simply don't accumulate enough mass for the core to reach hydrogen fusion temperatures. The core gets warm, it gets dense, but it never gets hot enough for sustained fusion to begin. The gravitational squeeze just isn't strong enough, and without fusion to generate outward energy, the object settles into a dim, cooling twilight. It glows faintly from the heat of its own formation, but it is not fusing hydrogen. It is not a star. This is a brown dwarf. The obvious question is, how much mass do you actually need? Where exactly is the dividing line between a star that fuses hydrogen and a brown dwarf that doesn't? The answer is roughly 75 times the mass of Jupiter. That might sound like an enormous amount, and by planetary standards, it absolutely is. Jupiter itself is the largest planet in our solar system. Its diameter stretches about 86,000 miles. Its mass is 318 times that of Earth. Stack 75 Jupiters together, and you have a truly staggering quantity of material. But here's the paradox. In stellar terms, 75 Jupiter masses is tiny. It works out to only about 7.5% of the mass of our Sun. That's the threshold. If a collapsing fragment gathers at least 75 Jupiter masses, it will sustain hydrogen fusion and become a true star. Specifically a small, dim, cool red dwarf sitting at the very bottom of the main sequence. If it falls below that line, it becomes a brown dwarf instead. Think about how thin that boundary really is. 7.5% of the Sun's mass is all that separates success from failure. An object with 76 Jupiter masses crosses the threshold and gets to be a star. An object with 74 does not. They form the same way. They went through the same collapse. They gathered mass through the same process. But one crossed the line and the other didn't. One lights up and shines for trillions of years. The other slowly fades into cold darkness. It's worth noting that this threshold isn't a perfectly sharp number. It depends somewhat on the chemical composition of the object. Objects with more heavy elements, what astronomers call higher metallicity, have a slightly different threshold than objects made of nearly pure hydrogen and helium. The presence of heavier elements changes how the gas absorbs and radiates energy, which shifts the internal temperatures needed for fusion. But 75 Jupiter masses is a reliable working number for most situations. So what exactly is a brown dwarf like? Let me paint a clearer picture, because these objects are genuinely fascinating in their own right, even before we get to the question of merging them. A brown dwarf sits in the mass range between about 13 Jupiter masses at the low end and roughly 75 Jupiter masses at the high end. Below 13 Jupiter masses, you're firmly in planet territory. Above 75, you have a true star. Brown dwarfs occupy the strange middle ground. They're often called failed stars, and there's truth in that label. They form the same way stars do, through gravitational collapse of a gas cloud. They went through the same protostellar phase. They just didn't gather enough mass to finish the job. But calling them failures is also a little unfair, because brown dwarfs are not entirely inert. They're not just cold lumps of gas doing nothing. They actually produce some energy through fusion, just not the sustained hydrogen fusion that defines a real star. Here's what happens. While a brown dwarf can't sustain ordinary hydrogen fusion, the kind that powers our sun, it can fuse deuterium. Deuterium is a heavier version of hydrogen. A normal hydrogen nucleus is just a single proton. Deuterium has one proton and one neutron stuck together. This makes deuterium easier to fuse because it requires lower temperatures and pressures than ordinary hydrogen. The threshold for deuterium fusion is only about 13 Jupiter masses, which is exactly why 13 Jupiter masses marks the lower boundary of the brown dwarf range. Anything above 13 Jupiter masses fuses deuterium. Anything above 75 fuses ordinary hydrogen. Brown dwarfs are the objects stuck in between. This is why astronomers consider brown dwarfs to be fundamentally different from planets. even though they exist in a similar mass range. A planet like Jupiter never fuses anything. It has no nuclear reactions occurring in its core. A brown dwarf, even the least massive one, fuses deuterium. It participates in nuclear physics. It generates energy through the same kind of process that powers stars, just with a different, much rarer fuel. This distinction is meaningful because it connects brown dwarfs to the world of stellar physics rather than planetary science. When a brown dwarf first forms while it's still hot from gravitational contraction, it fuses whatever deuterium exists in its core. This generates some energy and keeps the brown dwarf glowing. But the problem is that deuterium is incredibly rare compared to ordinary hydrogen. Only about 1 in every 40,000 hydrogen atoms in a typical gas cloud is deuterium. The fuel supply is minuscule. A brown dwarf burns through its deuterium in roughly 10 million to a few 100 million years, depending on its mass. After that, the fusion stops. Heavier brown dwarfs, those above about 65 Jupiter masses, can also burn lithium for a brief period. Lithium fusion requires higher temperatures than deuterium, so only the more massive brown dwarfs manage it. But lithium is even rarer than deuterium, so this fuel source runs out quickly too. Once the deuterium and lithium are gone, that's it. No more fuel. From that point on, the brown dwarf simply radiates away the heat it accumulated during its formation and its brief fusion phase. It cools, slowly, steadily, irreversibly. A young brown dwarf might have the surface temperature of roughly 4,000 degrees Fahrenheit, warm enough to glow a dim red. Over hundreds of millions of years, it cools to about 2,000 degrees. Over billions of years, it cools further, eventually reaching temperatures you might find in a kitchen oven, then a cup of coffee, then room temperature. In the far future, over timescales longer than the current age of the universe, a brown dwarf will cool until it becomes essentially invisible. A dark, cold object drifting silently through space, barely warmer than the cosmic background. Astronomers have actually built a classification system around this cooling process, because a brown dwarf doesn't just get dimmer as it ages. Its appearance fundamentally changes. The hottest, youngest brown dwarfs, those with surface temperatures above about 3,000 degrees Fahrenheit, are classified as L dwarfs. These objects glow a deep red or magenta. Their atmospheres contain clouds of iron and silicate dust, exotic mineral clouds that would be unimaginable on any planet in our solar system. As an L dwarf cools over hundreds of millions of years, those mineral clouds sink below the visible atmosphere, and methane begins to dominate. The object transitions into a T dwarf. T dwarfs are cooler, with surface temperatures between roughly 500 and 2,000 degrees Fahrenheit. They glow not red, but a dim, eerie magenta, and their spectra are dominated by the chemical fingerprints of methane and water vapor. They look more like extremely hot versions of Jupiter's atmosphere than anything you'd associate with a star. Cool further still, below about 500 degrees Fahrenheit, and you enter the realm of Y dwarfs. These are the coldest brown dwarfs ever detected, with some having surface temperatures not much warmer than a cup of coffee. Cooler than your kitchen oven at its lowest setting. Y dwarfs are so faint that discovering them required the most sensitive infrared space telescopes ever built. They emit almost no visible light at all. They glow only in the deepest infrared, wavelengths your eyes can't even see. This classification system, L then T then Y, isn't describing different types of objects. It's describing the same type of object at different stages of its life, An L-dwarf will eventually cool into a T-dwarf, which will eventually cool into a Y-dwarf. It's a one-way journey from warm to cold, from dim to dimmer to nearly invisible. Every brown dwarf is on this path. The only question is how far along it has travelled. Now, here's something about brown dwarfs that surprises most people when they first hear it. Despite spanning a huge range of masses, from 13 all the way up to 75 Jupiter masses, brown dwarfs are all roughly the same physical size. They're all about the diameter of Jupiter, give or take maybe 20%. A brown dwarf with 15 Jupiter masses and one with 70 Jupiter masses are both roughly 90,000 miles across. They look about the same size from the outside, even though one is nearly 5 times more massive than the other. How is that possible? The answer involves a quantum mechanical effect called electron degeneracy pressure. In a normal gas, adding more material makes the object bigger. More stuff, more volume, makes sense. But inside the incredibly dense interiors of brown dwarfs, electrons are packed so tightly together that quantum mechanics takes over. A fundamental rule of quantum physics, called the Pauli exclusion principle, prevents 2 electrons from occupying the same quantum state. This creates an outward pressure that resists further compression. Think of it like trying to pack more people into an already crowded elevator. At first, adding one more person just makes things more cramped, but eventually the elevator is so packed that people are physically resisting being pushed closer together. The crowd pushes back against anyone trying to squeeze in. That resistance is roughly analogous to degeneracy pressure. The electrons in a brown dwarf's interior are packed so tightly that quantum mechanics prevents them from being compressed further. The strange result is that adding more mass to a brown dwarf makes it denser without making it much larger. In some cases, adding mass actually makes the brown dwarf slightly smaller, because gravity squeezes the degenerate material more tightly. This is completely different from how everyday objects behave. On Earth, pile more stuff together and it gets bigger. In the world of brown dwarfs, more mass can mean a smaller object. This means that if you could somehow observe a brown dwarf up close, it would look remarkably similar to Jupiter. Roughly the same size, roughly spherical, with bands and layers in its atmosphere. But the atmosphere of a brown dwarf is far more exotic. Instead of the ammonia and water clouds you find on Jupiter, a brown dwarf's atmosphere might contain clouds of iron droplets or silicate dust. Minerals that exist as gases in the brown dwarf's hotter interior condense into clouds as they rise to cooler altitudes. Some brown dwarfs may experience weather where it literally rains molten iron. These are genuinely alien worlds, even if they look about the same size as the biggest planet in our solar system. There's another important distinction that trips people up. Brown dwarfs are not just big planets. They might seem similar at first glance. Jupiter is a big ball of gas, and a brown dwarf is an even bigger ball of gas. But the critical difference lies in how they formed. Jupiter formed inside a disk of gas and dust orbiting the young sun. It built up a solid core of rock and ice first, then gravitationally attracted a massive envelope of hydrogen and helium gas from the surrounding disk. Brown dwarfs form differently. They collapse directly from a fragment of a molecular cloud, the same way stars do. They don't need a pre-existing star to form around. They are independent objects, born through the same gravitational collapse that creates real stars. This distinction matters because it produces different internal structures. A brown dwarf formed from a collapsing cloud is essentially all hydrogen and helium, thoroughly mixed from its violent formation. A gas giant planet has layers with heavier elements concentrated toward a dense core. These structural differences will become critically important later in our story, when we start asking whether a merged brown dwarf can ignite hydrogen fusion. The concept of brown dwarfs has been around longer than most people realize. Astrophysicists predicted their existence decades before anyone found one. In 1962 and 1963, an astronomer named Shiv Kumar published calculations showing there should be a minimum mass to form hydrogen-burning stars. He worked out the physics of stellar interiors and predicted that objects below a certain mass threshold would never achieve sustained core fusion. They would form like stars, but fail to ignite. In 1975, the astronomer Jill Tarter proposed the name brown dwarf, and it stuck. Brown isn't really their colour. Young ones actually glow deep red or magenta, but the name captured the idea of something dim and in between, caught in the space between the red dwarfs, which are the smallest true stars, and the darkness of complete failure. For 3 decades after the theoretical predictions, nobody could actually find one. Brown dwarfs are dim. Even the youngest, hottest ones are thousands of times fainter than the sun. Spotting one is like searching for a dying ember in a dark forest from miles away. It wasn't until 1995 that the first confirmed brown dwarf was finally discovered. A team of astronomers found a faint companion orbiting a nearby red dwarf star called Gliese 229. The companion had a surface temperature of only about 1250 degrees Fahrenheit and a mass well below the hydrogen burning threshold. It was unmistakably a brown dwarf. Since those first discoveries, astronomers have found hundreds more. The real breakthrough came with infrared surveys, large-scale sky searches using telescopes designed not to detect visible light, but to pick up the faint heat glow that brown dwarfs emit. Because brown dwarfs are so cool compared to true stars, most of their energy comes out as infrared radiation, wavelengths of light that are invisible to human eyes but detectable by specialized instruments. Ground-based infrared surveys were the first to uncover brown dwarfs in significant numbers, scanning large swaths of the sky and identifying objects that were bright in infrared but invisible or nearly invisible in ordinary light. Then space-based observatories took the search to another level. The Spitzer Space Telescope, operating from orbit where Earth's atmosphere couldn't interfere with the faint infrared signals, discovered some of the coolest and most distant brown dwarfs known. But perhaps the most productive brown dwarf hunter was a space telescope called WISE, which stands for Wide Field Infrared Survey Explorer. WISE surveyed the entire sky in infrared wavelengths and discovered hundreds of previously unknown brown dwarfs, including some of the coldest white dwarfs ever found, objects with surface temperatures barely warmer than a summer day on Earth. These discoveries were only possible because astronomers stopped looking for light and started looking for heat. What these surveys revealed is that brown dwarfs are astonishingly common. Some estimates suggest there might be as many brown dwarfs in the Milky Way as there are true stars. Billions upon billions of failed stars, quietly cooling in the darkness, invisible to the naked eye, scattered among the bright points of light we see when we look up on a clear night. And here's where we arrive at the setup for tonight's central question. Brown dwarfs don't always form alone. When a molecular cloud collapses, The process is messy and chaotic. As a clump of gas falls inward under its own gravity, turbulence within the flow can carve the stream into separate fragments, each one continuing to collapse independently. Sometimes a collapsing core splits into two nearly equal pieces. Other times, smaller fragments form alongside larger ones. If both fragments end up with masses below the hydrogen burning threshold, you get two brown dwarfs. And if they remain close enough together, they'll be gravitationally bound to each other, orbiting their common center of mass in what astronomers call a binary system. Binary systems are extremely common throughout the universe. Roughly half of all sun-like stars in the Milky Way exist in binary or multiple star systems. Brown dwarfs form binaries too, though less frequently. Surveys suggest that somewhere between 10 and 20% of brown dwarfs have companions, and many of those companions are themselves brown dwarfs. There's another way these pairs can form as well. Two separately born brown dwarfs can encounter each other in a dense star-forming region and become gravitationally captured, though this requires a third body to carry away excess energy. It's rare, but in the crowded environments of stellar nurseries, it does happen. What makes some brown dwarf binaries particularly interesting is how tightly they orbit each other. Astronomers have discovered pairs with orbital periods of just a few days. At those separations, the two objects are only a few million miles apart, sometimes less than the distance from Mercury to the Sun. They're remarkably close. Close enough that gravity doesn't just hold them in orbit, it begins to distort them. Each brown dwarf raises a tidal bulge on the other, pulling it slightly out of round, deforming its shape in the same way the moon raises tides in Earth's oceans, except far more dramatically. Astronomers have been building a growing catalogue of these tight brown dwarf binaries for years now. Each newly discovered system adds to our picture of how these objects pair up and how their orbits behave over time. Some of the tightest known pairs orbit so rapidly and so closely that they complete a full revolution in less than a single Earth day. At those speeds and separations, the two objects are practically touching in astronomical terms. The gravitational interaction between them is intense, each one feeling the other's pull not as a gentle tug, but as a constant, inescapable force, reshaping it from the inside out. And these tidal interactions don't merely reshape the objects, they slowly change the orbit itself. Tides create friction inside each brown dwarf, converting orbital energy into heat. As energy drains from the orbit shrinks. The two brown dwarfs spiral slightly closer together. The tidal forces strengthen. The friction increases, more energy drains. The orbit shrinks further. It's a slow, relentless feedback loop. This process is agonizingly slow by human standards. Millions of years, possibly billions. But in a universe that is 13.8 billion years old, there's been plenty of time for some brown dwarf binaries to reach the point of no return. Imagine the scene. Two objects, each one roughly the size of Jupiter but tens of times more massive, orbiting each other in the dark emptiness between bright stars. Each one individually too small to sustain the hydrogen fusion that would make it a true star. Each one destined, on its own, to slowly cool and fade into nothingness over billions of years. Failed stars, objects that came close but fell short, and now they're locked together in a gravitational embrace, spiraling closer with every orbit, century after century, millennium after millennium. This isn't just a hypothetical thought experiment. Astrophysicists have modeled these scenarios using sophisticated computer simulations. They've calculated the physics of what happens when two dense substellar objects are driven together by orbital decay. The simulations reveal a process that is violent, complex, and full of surprising details. Material heats up, shockwaves ripple through the merging bodies, angular momentum gets redistributed in ways that change the shape and spin of the resulting object. Mass gets flung outward. The merged remnant doesn't just settle quietly into a bigger version of what it was before. It goes through a dramatic physical transformation that could, under the right conditions, change its fundamental nature. But all of that comes later in our story. For now, what matters is the setup. Two brown dwarfs, a tight binary, a slow spiral inward. And the question that drives everything we're about to explore is both simple and extraordinary. If neither one alone had enough mass to become a star, could the two of them together finally succeed? Could two failures add up to one success? So we have our two brown dwarfs, two objects born in the same collapsing cloud, gravitationally bound to each other, orbiting their common center of mass in the cold darkness between brighter stars, each one individually too small to sustain hydrogen fusion, each one fading slowly, radiating away the heat of its formation with no nuclear furnace to replenish it. Alone, each one is destined to become cold and dark over billions of years. But they're not alone. They have each other. And the fact that they're in a binary, locked together by gravity, changes everything about their future. Now, the obvious assumption most people make about a binary system like this is that it should be stable. Two objects orbiting each other in the vacuum of space, where there's no friction, no air resistance, nothing to slow them down. In a perfectly idealized universe, 2 point-like masses orbiting each other would continue doing so forever. Their orbit would never change. They would circle each other for eternity in a precisely repeating loop, like a perfectly wound clock that never runs down. But here's the thing. We don't live in a perfectly idealized universe. Brown dwarfs aren't point-like masses. They're real physical objects with real structure. They're balls of gas and partially degenerate matter, roughly the size of Jupiter but far denser. They have interiors that respond to gravitational forces. They have surfaces that can be deformed, and those properties introduce effects that slowly, relentlessly drain energy from the orbit over enormous stretches of time. The most important of these effects is something called tidal dissipation. And to understand it, you first need to understand tides. You already know about tides on Earth. The moon's gravity pulls on our planet, but it doesn't pull equally on every part of Earth. The side of Earth facing the moon gets pulled a little harder because it's closer. The side facing away gets pulled a little less because it's farther. This difference in gravitational pull across the diameter of our planet is called a tidal force. The result is that Earth gets slightly stretched along the line connecting it to the moon, bulging outward on both the near side and the far side. The oceans respond to this stretching more visibly than the solid rock does, which is why we see ocean tides rising and falling twice a day as Earth rotates beneath the tidal bulges. The key detail is this. Earth rotates faster than the moon orbits. Earth completes a full rotation in about 24 hours, but the moon takes roughly 27 days to complete an orbit. Because Earth is spinning faster than the moon orbits, friction between the water and the ocean floor drags the tidal bulge slightly ahead of the line connecting Earth to the moon. The bulge doesn't point exactly at the moon. It gets carried slightly forward by Earth's rotation. This misaligned bulge has consequences. Because the bulge has mass, its gravity pulls on the moon. And since the bulge is slightly ahead of the moon's position, that gravitational pull has a tiny forward component, accelerating the moon in its orbit. This pushes the moon to a slightly higher orbit, which is why the moon is drifting away from Earth at about 1.5 inches per year. At the same time, the moon's gravity pulls back on the misaligned bulge, applying a torque to Earth, slowing its rotation. That's why Earth's days are getting longer, very gradually, by about 2 milliseconds per century. The energy to push the moon outward and slow down Earth's rotation has to come from somewhere. It comes from the interaction between the rotating body and the tidal bulge. The friction between the sloshing oceans and the ocean floor converts some of that energy into heat. This process, the conversion of orbital and rotational energy into heat through tidal friction, is tidal dissipation. And it's happening right now, constantly, in the Earth-Moon system. Now take that same process and apply it to a binary brown dwarf system, except turn up the intensity by orders of magnitude. 2 brown dwarfs in a type binary are much closer together relative to their sizes than Earth and the Moon are. The tidal forces between them are correspondingly much stronger. Each brown dwarf raises an enormous tidal bulge on the other. Not the subtle ocean swells we see on Earth, but deep structural deformations. The entire body of each brown dwarf gets distorted, stretched into a slightly egg-like shape, pointing toward its companion. And because these are gaseous, fluid objects rather than rigid, rocky planets, the deformation can be substantial. Here's where the energy drain begins. If the brown dwarfs are spinning at rates different from their orbital period, and they almost certainly are when the binary first forms, then the tidal bulges are misaligned with the line connecting the 2 objects. Just like Earth's ocean tides are misaligned with the Earth-Moon line. The rotation carries the bulge slightly ahead or behind, and the companion's gravity tugs on that misaligned bulge, creating friction. That friction converts energy from the orbit and the spin into heat. The internal friction in a brown dwarf is not like water sloshing against a rocky ocean floor. It's far more subtle. Brown dwarfs are fluid throughout. They have no solid surface. The tidal deformation creates currents and flows inside the brown dwarf. Turbulent motions that generate heat through viscous friction. In some cases, the tidal forcing can excite oscillation modes, natural vibration frequencies of the brown dwarf that dissipate energy particularly efficiently. Think of it like pushing a child on a swing. If you push at the right frequency, matching the swing's natural period, the energy transfer is very efficient. Tidal forces can similarly resonate with internal oscillation modes, pumping energy into them, which then gets converted to heat. The net result is the energy drains steadily from the orbit. And when energy leaves an orbit, the orbit shrinks. The 2 objects move closer together. Their orbital period gets shorter. They spin around each other faster. And here's the cruel feedback. As the orbit shrinks, the tidal forces get stronger, because the objects are now closer. Stronger tidal forces mean more deformation, more friction, more energy dissipation, which makes the orbit shrink faster, which makes the tidal forces even stronger. It's a positive feedback loop, a slow motion death spiral that accelerates over time. In the early stages, when the binary is relatively wide, This process is incredibly slow. It might take billions of years for the orbit to shrink noticeably, but as the objects get closer, the rate of orbital decay increases. What took billions of years initially might take only millions of years later, and then hundreds of thousands, and then less. The closer they get, the faster they fall. Tidal dissipation is the dominant mechanism for driving close brown dwarf binaries toward merger. But it's not the only one. There are other processes that can help steal energy and angular momentum from the orbit. One of these is magnetic braking. Brown dwarfs, especially younger ones, can have surprisingly strong magnetic fields. These magnetic fields interact with any ionized gas in the environment, and more importantly, with any wind of charged particles the brown dwarfs might be emitting. When a magnetized object loses material through a wind, that material carries angular momentum away from the system. The material escapes along the magnetic field lines, which act like long levers, amplifying the angular momentum loss. It's like a figure skater extending their arms while spinning. The extended arms carry more angular momentum per unit mass than the body alone. When material flies off along extended magnetic field lines, it carries disproportionately large amounts of angular momentum away, slowing the system. For ordinary stars, magnetic braking is a major driver of spin down and orbital evolution in close binaries. For brown dwarfs, the effect is likely weaker because their winds are less powerful, but it's not zero, and over hundreds of millions or billions of years, even a small drain adds up. Another contributor is gravitational wave radiation. Einstein's general theory of relativity predicts that any two masses orbiting each other will emit gravitational waves, ripples in the fabric of space-time itself. These waves carry energy away from the system, causing the orbit to shrink. For massive, compact objects like neutron stars or black holes in tight orbits, gravitational wave emission is extremely powerful. It's what drives neutron star mergers, events so violent they produce flashes of light, visible across the universe. For brown dwarf binaries, a gravitational wave emission is extraordinarily weak. Brown dwarfs are not dense enough, not massive enough, and not close enough for this effect to matter much, at least not in the early stages. A pair of brown dwarfs in a typical closed binary might lose less energy to gravitational waves in 1 billion years than a single lightning bolt releases on Earth. It's negligible for most of the binary's life. But here's the thing. Gravitational wave emission is always present, always draining energy, and it becomes more significant as the orbit shrinks and the orbital velocities increase. In the very final stages of inspiral, when the two objects are extraordinarily close, gravitational radiation can become a meaningful contributor to the orbital decay that's already being dominated by tidal effects. It's a small nudge that adds to the larger forces already at work. There's also a fourth way a brown dwarf binary can be driven toward merger, and it involves the gravitational influence of a third body. Brown dwarf binaries don't exist in perfect isolation. They're embedded in a galaxy with nearby stars, and some brown dwarf binaries are actually part of triple or higher order systems, where a more distant companion star orbits the inner pair. When a distant third body orbits a closed binary at an angle, its gravity can periodically pump up the eccentricity of the inner orbit. Eccentricity measures how elongated an orbit is. A perfectly circular orbit has zero eccentricity. A highly elongated, stretched out ellipse has high eccentricity. When the third body increases the inner orbit's eccentricity, the two brown dwarfs swing closer together at their closest approach, even though their average separation stays roughly the same. And those closer approaches dramatically amplify tidal forces, because tidal forces depend extremely steeply on distance. Cut the distance in half, and the tidal force increases by a factor of roughly 8. These periodic close approaches can dump enormous amounts of tidal energy into the system, accelerating the orbital decay far beyond what tidal friction alone would accomplish. A third body can also occasionally deliver a gravitational kick that suddenly changes the inner binary's orbit, pushing the two brown dwarfs onto a more tightly bound trajectory. In crowded stellar nurseries where brown dwarfs are born, encounters with passing stars or other young objects can perturb the binary, sometimes tightening it, sometimes disrupting it entirely. The binaries that survive these encounters and get tightened are the ones most likely to eventually merge. Now, before we go further, we need to talk about something that is absolutely central to this entire story. It comes up again and again. It determines the shape of the merger, the fate of the remnant, and the answer to whether a star can be born from the collision. That something is angular momentum. Angular momentum is one of the most fundamental conserved quantities in physics. In simple terms, it measures how much rotational motion a system has. A spinning top has angular momentum. A planet orbiting a star has angular momentum. Two brown dwarfs circling each other have orbital angular momentum, and each one also has spin angular momentum from its own rotation. The critical thing about angular momentum is that it doesn't just disappear, it's conserved. If no outside force acts to remove it, the total angular momentum of a system stays constant. You can redistribute it, transfer it from one place to another, convert orbital angular momentum into spin angular momentum, but you can't destroy it. It has to go somewhere. This is why the two brown dwarfs can't simply fall straight toward each other and collide head-on. In a science fiction movie, you might imagine two objects in space hurtling directly at each other, meeting in a spectacular crash. But that's not how orbiting objects work. They have angular momentum. They're moving sideways as well as inward. That sideways motion prevents a direct plunge. Instead of falling straight in, each object keeps missing the other, swinging around in an orbit. To actually bring them together, you have to remove angular momentum from the system. And that's a slow, difficult process. Every mechanism we've discussed, tidal dissipation, magnetic braking, gravitational wave emission, third body interactions, they all work by removing angular momentum from the orbit. They're all draining rotational motion from the system, allowing the orbit to tighten. But none of them remove angular momentum quickly or completely. Even as the orbit shrinks, the system retains a significant amount of angular momentum. And this remaining angular momentum will profoundly shape what happens during and after the merger. As the orbit shrinks and the two brown dwarfs draw closer, the tidal distortion becomes increasingly dramatic. Remember, at wider separations, the tidal bulges were relatively subtle. Each brown dwarf was slightly egg-shaped, stretched gently toward its companion. But as the separation decreases, the tidal forces grow enormously. The objects become more and more elongated. Their shapes shift from slightly out of round to visibly distorted, like softballs being pulled into footballs. The side of each brown dwarf facing its companion bulges outward dramatically, while the far side bulges outward in the opposite direction. At some point, the distortion becomes so extreme that we need a new framework to describe what's happening. This is where we introduce a concept that astronomers use constantly when studying closed binary systems. It's named after the 19th century French mathematician Edouard Roche, and it's called the Roche lobe. Imagine drawing a three-dimensional boundary around each brown dwarf. Inside that boundary, material is gravitationally bound to that particular brown dwarf. Any gas or matter inside the boundary stays with that object. It orbits that object, falls onto that object, belongs to that object. Outside the boundary, the gravitational allegiance shifts. Material might be captured by the companion, or it might escape the system entirely. This boundary is the Roche lobe. In a binary system, each object has its own Roche lobe. The two lobes touch at a single point between the two objects, a location called the L1 point, or the inner Lagrange point. This is the spot where the gravitational pull of both objects, combined with the centrifugal effect of the orbital motion, exactly balances. It's a gravitational saddle point. A tiny nudge in either direction sends material falling toward one brown dwarf or the other. When the two objects are far apart, each Roche lobe is enormous compared to the object sitting inside it. The brown dwarf occupies only a small fraction of its Roche lobe. There's plenty of room, but as the orbit shrinks, the Roche lobes shrink too. They close in around each object like tightening walls. And here's the crucial moment. If one brown dwarf expands, or if the Roche lobe shrinks enough, the surface of the brown dwarf can reach the boundary of its Roche lobe. When that happens, the brown dwarf fills its Roche lobe. And when a brown dwarf fills its Roche lobe, something remarkable begins. Material from the outer layers of that brown dwarf, the gas sitting right at the surface nearest to the companion, is no longer gravitationally bound to it. That material sits right at the L1 point, balanced on a gravitational knife edge. And any tiny perturbation, any slight push, sends it streaming across the gap toward the companion. This is the onset of mass transfer. A thin stream of gas begins flowing from one brown dwarf to the other, threading through the L1 point like water pouring through a narrow gap between two hills. The stream doesn't fall straight onto the companion. Remember angular momentum. The transferred material carries angular momentum from the orbit, so it curves as it falls. Instead of hitting the companion dead on, it swings around and often forms a swirling disk of material around the receiving brown dwarf. This disk is called an accretion disk, and it's a common feature in any binary system undergoing mass transfer. The gas in the accretion disk gradually spirals inward, losing energy through friction and viscosity, eventually settling onto the surface of the receiving brown dwarf. The receiver gains mass. The donor loses mass. The dynamics of the system shift. Now here's where the story takes a decisive turn. Whether the mass transfer remains gentle and controlled, or whether it runs away into a catastrophic merger, depends on a critical question. How does the donating brown dwarf respond to losing mass? In some binary systems involving ordinary stars, mass transfer is stable. The donor loses a little mass. It adjusts. It shrinks slightly within its Roche lobe. The transfer slows down or reaches a steady rate. The system can persist in this state for millions of years, with material flowing gently from one object to the other in a controlled, sustainable way. The binary evolves slowly, changing its mass ratio over time, but never merging. But brown dwarfs are different from ordinary stars. Their interiors are partially degenerate. Remember electron degeneracy pressure, the quantum mechanical effect that makes all brown dwarfs roughly the same size, regardless of mass. This degeneracy has a counterintuitive consequence for mass transfer. When a normal star loses mass from its surface, it typically shrinks. Less mass means weaker gravity, and the star contracts to a new, smaller equilibrium. But a partially degenerate object like a brown dwarf can behave in the opposite way. When you remove mass from a degenerate object, the degeneracy pressure, which was holding the object at a certain size, doesn't decrease proportionally. The object can actually expand as it loses mass, take material away, and the brown dwarf puffs up. This creates a catastrophic feedback loop. The donor brown dwarf loses mass through the L1 point. Instead of shrinking away from its Roche lobe boundary and slowing the transfer, it expands. It pushes even more material beyond the Roche lobe boundary. The transfer rate increases. The donor expands further. More material overflows. The transfer accelerates. It becomes a runaway process. This is unstable mass transfer, and for many brown dwarf binary configurations, it is the expected outcome. Once the donor fills its Roche lobe and mass transfer begins, the partially degenerate nature of the brown dwarf's interior means the transfer cannot be controlled. It runs away. Material floods across the L1 point in ever-increasing quantities. Within a relatively short time, astronomically speaking, perhaps thousands of years or even less, the system transitions from gentle mass transfer to violent contact. But even during runaway mass transfer, angular momentum refuses to be ignored. The transferred material carries angular momentum. The accretion disk around the receiving brown dwarf stores angular momentum. The orbital motion still resists a simple head-on plunge. The system doesn't collapse instantaneously. Instead, it spirals. The two objects draw closer and closer, their surfaces now nearly touching, their shapes grotesquely distorted by tidal forces. Each one is stretched into a teardrop shape, pointed at the other, with streams of gas flowing between them and around them. At some point, the separation becomes so small that the two objects physically touch. Their outer envelopes make contact. Gas flows not just through a narrow stream at the L1 point, but across a broad contact surface where the two objects press against each other. The system has entered what astronomers call a contact binary. Two objects sharing a common envelope of gas, their surfaces merged into a single peanut-shaped or dumbbell-shaped structure, still orbiting their common center of mass, still spinning, still carrying angular momentum. And even now, the process doesn't stop. The contact binary continues losing orbital energy through friction and tidal interactions within the shared envelope. The two dense cores at the center of the dumbbell spiral closer still. Material from the envelope gets heated by the friction, puffing outward. Some gas near the equator, where the rotational velocity is highest, may gain enough speed to escape entirely, carrying angular momentum away from the system and allowing the cores to fall inward even faster. The timescale for this final phase is remarkably short compared to the billions of years the orbital decay took. The slow spiral inward might have lasted for hundreds of millions or billions of years. But once contact is established, the actual merger of the two cores can happen in a matter of years or even months. The transition from a slowly decaying binary to a fully merged single object is dramatic. It's like watching a ball roll slowly across a flat table for hours. then suddenly reach the edge and plummet. Imagine being able to watch this process in time lapse. For billions of years, almost nothing visible happens. Two dim objects circle each other in the dark, their orbit tightening imperceptibly. Then the pace picks up. The objects visibly distort. A stream of glowing gas appears between them. The stream widens. The objects swell, elongate, reach toward each other. Their surfaces touch. They form a single rotating mass, glowing brighter now from the frictional heating, surrounded by a disk of expelled gas. The structure pulses, contracts, and the two cores plunge together. What you're left with, in the immediate aftermath, is something that didn't exist moments before. Not two brown dwarfs anymore. One object, rapidly spinning, enormously hot, bloated far beyond its equilibrium size, radiating furiously as it tries to shed the tremendous energy dumped into it by the merger. A brand new astrophysical object that has to figure out what it is. Is it still a brown dwarf? Is it something more? Has the combination of two failed stars produced enough mass, enough pressure, enough heat at the core for hydrogen fusion to finally ignite? That depends on what happens next. The two brown dwarfs have made contact. After millions or billions of years of slow orbital decay, after their Roche lobes shrank around them and mass transfer ran away into a flood, after their surfaces touched and they entered a shared envelope, the two dense cores at the heart of this dumbbell-shaped structure have finally plunged together. This is the merger, and it is one of the most physically complex events that can happen to substellar objects. Let's walk through what actually happens, step by step, because the physics of this collision determines everything that follows. It determines the temperature, the density, the rotation rate, and the composition of the merged remnant. And those properties, in turn, determine whether the remnant can ever become a star. The first thing to understand is that this is not a gentle process. When two dense objects crash together at orbital velocities, the kinetic energy involved is enormous. By the time the two brown dwarf cores make final contact, they're moving at speeds of hundreds of kilometers per second relative to each other. Each one has a mass measured in tens of Jupiters. The kinetic energy of their collision is staggering, comparable to the gravitational binding energy of the objects themselves. When the outer layers of the two cores slam into each other, that kinetic energy doesn't just vanish. It has to go somewhere. And where it goes is into heat. The collision generates powerful shockwaves that ripple through both objects. A shockwave is a sudden, violent compression of material, a wall of pressure plowing through the gas at speeds faster than sound. When a shockwave passes through a region of gas, it compresses that gas dramatically and heats it up. The gas behind the shock front becomes enormously hot, far hotter than it was moments before. In the case of two merging brown dwarfs, these shock waves heat the material at the contact interface to temperatures far exceeding anything either object experienced on its own. Before the merger, a typical brown dwarf's interior might have temperatures of a few 100,000 to a few million degrees, depending on its mass and age. The shock heating during the merger can temporarily raise temperatures in the collision zone to tens of millions of degrees or more. This is significant because tens of millions of degrees is the range where hydrogen fusion becomes possible. The shock heating alone, without any gravitational contraction, can briefly push temperatures into the fusion regime at the collision interface. But, and this is important, shock heating is temporary. It's a burst of heat generated by the violence of the impact, not a sustained source of energy. The heated material will radiate that energy away and cool down unless something else maintains the temperature. Whether fusion can be sustained depends on conditions that develop later, after the remnant settles into a new equilibrium. Shock heating opens the door, but it doesn't keep it open. Now, let us talk about what happens to the material itself. Before the merger, each brown dwarf had its own distinct interior structure. Each one had its own core, its own layers, its own density profile running from a dense center to a thinner outer envelope. These two separate structures are now being smashed together. The merger doesn't simply stack one interior on top of the other in neat layers. Instead, the collision drives violent, turbulent mixing. Turbulence is chaotic, swirling fluid motion. When two fluid bodies collide at high speed, their interiors don't slide smoothly past each other. They develop instabilities at the contact surface. These instabilities, called Kelvin-Helmholtz instabilities, create rolls and vortices at the boundary between the two streams of material, like the curling waves you see when a fast-moving river meets a slower channel. The vortices grow, tangle, break apart, and generate smaller vortices, which themselves break apart into even smaller ones. The result is a cascade of turbulent mixing that stirs the two interiors together on progressively finer scales. This mixing has important consequences. It distributes heat throughout the merged object rather than concentrating it at the collision interface. It blends the chemical compositions of the two progenitors, homogenizing the hydrogen, helium, and trace heavier elements across the new interior. And it distributes angular momentum throughout the body, affecting how the remnant rotates. The mixing is not instantaneous. It takes time for the turbulence to penetrate deep into the cores. The densest central regions of each brown dwarf resist mixing more than the outer layers because they're denser and harder to stir. Simulations of brown dwarf mergers suggest that the cores may partially survive the initial collision as distinct dense knots embedded in a shared turbulent envelope. Over time, these knots are gradually eroded and mixed in, but the merger doesn't produce a perfectly uniform object right away. The remnant, at least initially, has a complicated and heterogeneous interior structure. Astrophysicists study these mergers using computer simulations. These simulations divide each brown dwarf into hundreds of thousands or even millions of tiny computational elements, each one representing a small parcel of gas. The simulation tracks how each parcel moves, heats up, cools down, and interacts with neighboring parcels under the influence of gravity, pressure, and hydrodynamic forces. The most common technique is called smoothed particle hydrodynamics, where each computational element is treated as a particle that interacts with its neighbors through smoothly varying forces. These simulations reveal a process that unfolds in stages. First, the outer envelopes make contact and begin to merge, forming the shared envelope we discussed earlier. Then the denser inner regions collide, generating the shockwaves and turbulent mixing we've been describing. The whole event, from first contact to the formation of a single merged body, typically takes only a few orbital periods of the original binary. That translates to hours or days. Compared to the billions of years the binary took to spiral inward, the actual merger is explosively fast. It's like watching a slow-motion fuse burn for ages, then the detonation happens in an instant. But let's be clear about something. This merger, while violent by brown dwarf standards, is not violent by the standards of the most extreme events in astrophysics. A supernova, the explosion of a massive star at the end of its life, releases roughly 10 to the power of 46 joules of energy in a fraction of a second. It can outshine an entire galaxy for weeks. A neutron star merger, the collision of two ultra-dense stellar corpses, produces gravitational waves detectable across the universe and generates enough energy to forge heavy elements like gold and platinum. A brown dwarf merger is nothing like that. The energies involved are many orders of magnitude smaller. Brown dwarfs are far less massive than the stars that produce supernovae, and they're far less dense than neutron stars. The energy released in a brown dwarf merger is comparable to a very small fraction of the gravitational binding energy of a single brown dwarf. It's enough to heat the merged object dramatically and puff it up to many times its original size. It's enough to generate a brief brightening that might be detectable with sensitive telescopes if you happen to be looking in the right direction at the right time. But it's not going to outshine a galaxy or be visible across the cosmos. This is actually part of the challenge of studying brown dwarf mergers. They're dim events involving dim objects. Even at their brightest during the actual merger, the combined luminosity of the system might briefly reach something comparable to a very faint star. Before and after the merger, the system is far dimmer. This means that identifying a brown dwarf merger in progress, or even finding the aftermath of one, requires knowing exactly where to look and having instruments sensitive enough to detect these faint signals. Now, we arrive at one of the most important aspects of the entire merger process: the role of angular momentum. We talked about angular momentum at length earlier, and for good reason. Angular momentum is the invisible hand that shapes every stage of this process, from the initial orbital decay to the final structure of the merged remnant. And during the merger itself, angular momentum becomes the dominant physical constraint. Before the merger, the system had orbital angular momentum from the two brown dwarfs circling each other. Each brown dwarf also had its own spin angular momentum from its individual rotation. When the two objects merge into one, all of that angular momentum has to go somewhere. It cannot be destroyed. The laws of physics absolutely forbid it. The total angular momentum of the system is conserved. So where does it go? Most of it goes into the spin of the merged remnant. Two objects that were orbiting each other are now one object that is spinning. And it's spinning fast. Extremely fast. The merged remnant inherits the angular momentum of the entire pre-merger binary system, and that's a lot of angular momentum. Let me put this in perspective. Consider the orbital velocity of the two brown dwarfs just before they merged. In a tight binary with a period of just a few hours, each brown dwarf is moving at hundreds of kilometers per second around the center of mass. That velocity, that enormous amount of sideways motion, doesn't disappear when the objects combine. It gets converted into rotational velocity. The merged remnant can end up spinning with surface velocities of tens or even hundreds of kilometers per second. For comparison, our sun rotates at about 2 kilometers per second at its equator. Jupiter rotates at about 12.5 kilometers per second. The merger remnant would be spinning many times faster than either. This has profound physical consequences. A rapidly spinning object experiences centrifugal effects. Material at the equator is flung outward by the rotation, resisting gravity's inward pull. If the spin is fast enough, the centrifugal effect at the equator can rival the gravitational pull. When that happens, the object can no longer hold itself together in a spherical shape. It distorts. It flattens at the poles and bulges at the equator, becoming an oblate shape, like a squished ball. If the spin is even faster, the object can become dramatically ablate, more like a thick disc than a sphere. And if the angular momentum is extreme enough, the equatorial material might actually exceed the escape velocity. Material at the equator would be flung off into space because the spin is simply too fast for gravity to hold it. This is exactly what simulations predict happens during and immediately after a brown dwarf merger. The merged remnant cannot simply settle into a nice, neat, stationary sphere. It has too much angular momentum for that. Instead, it forms a rapidly spinning, oblate, bloated structure. And because it can't contain all the angular momentum within a single body, some of that angular momentum gets exported outward through the ejection of material. This brings us to one of the most visually dramatic aspects of the merger: mass ejection. During the merger, material is flung outward from the system. This happens through several mechanisms. First, as the two objects are spiraled together and their shared envelope becomes rotationally unstable, gas near the equator of the rotating structure gets spun off like water flying from a wet, spinning wheel. Second, the shockwaves generated during the collision can accelerate pockets of gas to velocities exceeding the local escape speed, launching them away from the merger site. Third, once the merger remnant forms and begins spinning at near breakup speeds, material continuously leaks from the equatorial bulge, forming an expanding disk or torus of gas around the central object. How much material gets ejected? This depends on the specific parameters of the merger, the masses of the two brown dwarfs, the angular momentum of the pre-merger binary, the eccentricity of the orbit at the time of contact, and other factors. Simulations suggest that somewhere between a few percent and perhaps 10 or 15% of the total mass might be expelled during and immediately after the merger. In extreme cases, with very high angular momentum, the mass loss could be even larger. This ejected material doesn't just vanish, it forms a circumstellar disk around the remnant, a ring or torus of hot gas and eventually dust that gradually spreads outward, cools, and dissipates over time. This disk might be detectable. It would emit infrared radiation as it cools, creating a signature that astronomers could potentially identify. In fact, one way to search for the aftermath of a brown dwarf merger would be to look for substellar objects surrounded by unusual disks of warm material, disks that can't easily be explained by normal formation processes. The mass loss matters for another reason too. Every bit of material that gets ejected during the merger is mass that the remnant doesn't get to keep. If we're asking whether the merged object has enough mass to cross the hydrogen burning threshold and become a star, then every gram that escapes works against that goal. Two brown dwarfs with a combined mass of 80 Jupiter masses might produce a remnant with only 70 or 75 Jupiter masses if 10 or 15% of the total is lost. That could be the difference between a successful star and another failed attempt. The margin, as we'll see later, can be excruciatingly thin. Let's talk about what the immediate post-merger remnant actually looks like, because it is dramatically different from either of the two brown dwarfs that went into the collision. Before the merger, each brown dwarf was a relatively compact, cool, dense object, roughly the size of Jupiter, dim, slowly fading, old perhaps, and cold, a quiet failure drifting through space. The merger remnant is none of those things. It is hot. The shockwaves and turbulent mixing during the collision have dumped enormous thermal energy into the material. The interior temperatures are far higher than they were in either progenitor. The surface temperature has jumped as well, possibly reaching several thousand degrees, making the remnant glow brightly in the infrared and potentially even in visible red light. It is dramatically more luminous than either brown dwarf was before the merger, perhaps hundreds or thousands of times brighter, at least temporarily. It is bloated. The thermal energy injected by the merger has puffed the remnant up to many times the size of either original brown dwarf. Instead of being Jupiter-sized, the remnant might initially swell to several times Jupiter's radius. It's expanded like a balloon being inflated from the inside. The added heat gives the gas more thermal pressure, which pushes outward against gravity and supports a larger, more extended structure. It is rapidly spinning. As we discussed, the remnant has inherited the angular momentum of the entire binary system. It rotates at speeds that may approach the breakup limit, the maximum spin rate at which gravity can still hold the object together. This rapid rotation flattens it at the poles and stretches it at the equator, and it is out of equilibrium. This is perhaps the most important characteristic of all. The merged remnant is not in a stable state. It is not in thermal equilibrium, meaning the rate of energy generation inside does not match the rate of energy being radiated from the surface. It is not in hydrostatic equilibrium in its final form, meaning the balance between gravity pulling inward and pressure pushing outward hasn't settled into a steady configuration yet. It is still ringing, still sloshing, still adjusting from the violence of the collision. The object needs time, potentially a lot of time, to settle down. What happens next is a process called thermal relaxation, or more specifically, Kelvin-Helmholtz contraction. It's the same process that governs how any newly formed object adjusts to its own gravity when it lacks an internal energy source powerful enough to support itself indefinitely. Here's how it works. The hot, bloated remnant radiates energy from its surface. Photons carry heat away into space. As the object loses thermal energy, it has less pressure to support itself against its own gravity. So it contracts, it shrinks, but as it contracts, the gas gets compressed, and compression heats it up. This is the same effect you feel when you pump air into a bicycle tire. The pump gets warm because compressing the air converts gravitational potential energy into thermal energy. So the object contracts, heats up from the compression, radiates that heat away, contracts further, heats up again, radiates again. It's a slow, stuttering descent toward a more compact, denser state. Each cycle of contraction and radiation brings the remnant closer to its final equilibrium configuration. The process is like a ball bouncing down a staircase, losing energy with each bounce, settling lower and lower. The timescale for this thermal relaxation is not quick. For objects near the hydrogen-burning boundary, the Kelvin-Helmholtz timescale can be millions to tens of millions of years. That's fast by astronomical standards, a blink of an eye compared to the billions of years the binary took to spiral inward. But it's still an enormously long time by human reckoning. The remnant will spend millions of years slowly contracting, slowly cooling, slowly adjusting its internal structure. During this contraction phase, the internal temperatures and pressures at the center of the remnant steadily rise. The core gets hotter and denser as more and more material presses down on it. And this is where the critical question begins to take shape. As the core temperature climbs, it approaches the threshold for hydrogen fusion. If the remnant is massive enough, And if the contraction proceeds far enough, the core temperature may eventually reach roughly 3 million degrees Kelvin, the minimum needed for the proton-proton chain reaction to begin. This is the nuclear fusion reaction that powers the smallest, coolest red dwarf stars. But there's a catch. The thermal energy deposited by the merger is working against this process. The merger made the remnant hot. That extra heat provides extra pressure, which supports the remnant against gravitational contraction. A hotter object doesn't need to contract as much to support itself. So the merger heating actually delays the contraction. It's like trying to deflate a balloon that someone keeps blowing more air into. The remnant has to radiate away all that extra merger heat before it can contract to the densities and temperatures needed for sustained fusion. This means the remnant's path to possible stardom is not immediate. It doesn't merge and instantly start fusing hydrogen. It merges, puffs up, glows brightly for a while, then spends millions of years slowly contracting and cooling, radiating away the energy of the collision before conditions in the core have any chance of reaching the fusion threshold. The rapid rotation adds another layer of complexity. A spinning object experiences centrifugal effects that partially counteract gravity. At the equator, the centrifugal push reduces the effective gravity, making it harder for the object to contract in that direction. A rapidly spinning remnant can't contract symmetrically. It contracts more easily along the poles, where rotation has less effect than at the equator, where centrifugal force resists compression. This means the remnant doesn't settle into a sphere. It settles into an oblate shape, flattened at the poles and extended at the equator. The equatorial bulge remains puffed up, supported partly by centrifugal force. The core, sitting at the center, is compressed from the polar directions, but less so from the equatorial directions. The pressure distribution inside the remnant is not symmetric. It's shaped by the interplay of gravity, thermal pressure, and rotation. Over time, the rotation rate will decrease. The remnant loses angular momentum through several channels. The expelled disk carries some away. Magnetic fields threading through the remnant can couple to the disk or to any remaining wind of material, acting as a brake. Internal redistribution of angular momentum through turbulent viscosity can transfer spin from the core to the outer layers, where it can be more easily shed. Slowly, the remnant spins down. As the rotation slows, the centrifugal support weakens, and the remnant can contract further. The core gets denser and hotter. The path toward possible fusion continues. But the spin down, like the thermal relaxation, takes time. It is measured in millions of years, not thousands. So the picture that emerges is this. Immediately after the merger, you have a hot, bloated, rapidly spinning object, surrounded by a disk of ejected material. It looks nothing like either of the two brown dwarfs that created it. It's brighter, bigger, hotter, and spinning far faster. Over the following millions of years, it gradually cools, contracts, and spins down. The disk around it slowly disperses. The remnant settles toward a new equilibrium, its core steadily growing hotter and denser as contraction compresses the material. And as it contracts, the remnant approaches a moment of truth. There is a threshold waiting at the center. A temperature, a pressure, a condition that, if reached, will change everything about this object's future. If the core gets hot and dense enough, hydrogen fusion will ignite. Not the brief, limited deuterium burning that occurs in ordinary brown dwarfs, but sustained, self-regulating hydrogen fusion, the same process that powers our sun and every other star in the universe. If that happens, the remnant stops contracting. The energy from fusion provides the pressure needed to support the object against gravity indefinitely. It reaches a stable equilibrium. It becomes a star. But whether the core actually reaches that threshold depends on factors that are far more subtle than just total mass. It depends on how much mass was lost during the merger. It depends on the chemical composition. It depends on how much thermal energy the merger deposited and how long it takes to radiate that energy away. It depends on the degree of degeneracy in the core. It depends on how fast the remnant is spinning and how quickly it spins down. The answer, in other words, is not simple. Two failed stars have combined into one object. That object is slowly contracting toward its destiny. And the question of whether it will finally cross the threshold that each of its parents failed to reach is the question we'll answer next. So here we are. The moment the entire story has been building toward. Two brown dwarfs, each one individually unable to sustain hydrogen fusion, have spiraled together over millions or billions of years, collided in a violent merger, and produced a single hot, bloated, rapidly spinning remnant. That remnant is now slowly contracting, slowly radiating away the enormous thermal energy deposited by the collision, slowly spinning down as angular momentum is redistributed and shed. Deep in its core, temperatures and pressures are climbing as gravity squeezes the material tighter with each passing millennium. The question is simple. Can this merged object become a star? The first thing we need to examine is the mass budget, because nothing else matters if there isn't enough mass. Sustained hydrogen fusion, the kind that defines a true star, requires roughly 75 Jupiter masses. That's the threshold, the finish line that every brown dwarf individually failed to reach. So for the merged remnant to have any chance of becoming a star, the combined mass of the two progenitors, minus whatever mass was lost during the merger, has to land above that line. Let's think about the arithmetic. Brown dwarfs span a range from about 13 to 75 Jupiter masses. A merger between two brown dwarfs at the lower end of that range, say two objects of 20 Jupiter masses each, produces a combined mass of only 40 Jupiter masses. Even if zero mass is lost during the merger, that's nowhere close to 75. No amount of contraction or clever physics will turn 40 Jupiter masses into a hydrogen-burning star. The mass simply isn't there. The remnant will be a more massive brown dwarf than either progenitor, hotter and brighter for a while, but ultimately destined to cool and fade just like any other brown dwarf. It will be a bigger failure, but a failure nonetheless. For the merger to have any realistic shot at crossing the threshold, you need two brown dwarfs that are already individually close to the boundary. Think of objects in the range of 40 to 65 Jupiter masses each. Two brown dwarfs of 40 Jupiter masses give a combined mass of 80. Two of 50 give 100. Two of 65 give 130. These combined masses are comfortably above the 75 Jupiter mass threshold, at least on paper. But remember what we learned earlier. Some mass is ejected during the merger. The violence of the collision, the rapid rotation, the shockwaves, all of these conspire to fling material outward. Estimates from simulations suggest anywhere from a few percent to perhaps 15% of the total mass might be lost. Take two brown dwarfs of 40 Jupiter masses each. Combined, that's 80. Lose 10% and you're down to 72. That's below the threshold. The merger failed to produce enough mass for a star, even though the raw total was above the line. This illustrates how thin the margins can be. A combined mass of 80 Jupiter masses sounds like it should be enough. It's above the threshold. But if the merger is messy enough, if too much material gets flung away, the remnant might still fall short. The mass budget has to account not just for what goes in, but for what gets thrown out. On the other hand, 2 brown dwarfs of 50 Jupiter masses each give a combined mass of 100. Even losing 15% leaves 85 Jupiter masses. That's safely above the threshold. For sufficiently massive progenitors, the mass budget works out even with significant mass loss. The heavier the initial brown dwarfs, the more room there is for losses. So the mass budget is necessary but not sufficient. Having enough mass is the first requirement. Without it, nothing else matters. But having enough mass doesn't automatically guarantee success. Because, and this is the part most people never consider, the hydrogen burning threshold is not just about how much mass you have. It's about what that mass is made of, how it's arranged, and what happened to it during the merger. Let me explain why total mass alone doesn't tell the whole story. The 75 Jupiter mass threshold is often quoted as if it's a fixed universal number, but it's not. It shifts depending on the chemical composition of the object, specifically its metallicity, the proportion of elements heavier than hydrogen and helium. In a cloud of pure hydrogen and helium, with essentially no heavier elements, the hydrogen burning minimum mass is slightly lower, around 70 or 72 Jupiter masses. In a gas enriched with heavier elements, the kind of material you'd find in star-forming regions that have been enriched by previous generations of supernovae, the threshold shifts upward, potentially to 77 or even 80 Jupiter masses. Why does metallicity matter? Because heavier elements in the atmosphere and interior of the object change how it absorbs and radiates energy. Metals, in the astronomical sense, meaning anything heavier than helium, increase the opacity of the gas. Opacity is a measure of how difficult it is for photons to travel through the material. Higher opacity means photons get absorbed and re-emitted more often. They take longer to escape. The gas becomes a better insulator, trapping heat more effectively. Higher opacity changes the thermal structure of the object. It changes how quickly the interior can cool, how the temperature gradient is arranged from center to surface, and therefore how the core temperature relates to the total mass. The net effect is that objects with higher metallicity need slightly more mass to reach the same core temperature. The hydrogen burning threshold creeps upward. This means that 2 brown dwarfs formed in a metal-rich environment face a tougher challenge than 2 formed in a metal-poor one. Their combined mass has to be higher to cross a threshold that's been pushed upward by their own composition. It's like trying to clear a high jump bar that someone raised by an inch just because of the shoes you're wearing. Now, let's address something even more fundamental than composition. Something that makes a merged brown dwarf genuinely different from an object that simply formed with the same mass in the first place. That something is entropy. In thermodynamics, entropy is a measure of disorder, of how much thermal energy is distributed throughout a system. In astrophysics, when we talk about the entropy of a stellar or substellar object, we're essentially talking about how much heat is stored in the material and how that heat affects its structure. A high entropy object is hot, expanded, and puffy. A low entropy object is cool, compact, and dense. Here's why this matters so profoundly for our merged remnant. A brown dwarf that forms normally from a collapsing cloud starts out hot, then cools and contracts over time, gradually lowering its entropy. By the time it has settled into its mature state, its internal structure reflects a long history of slow cooling. Its interior is relatively cool and dense for its mass. Its entropy is low. Now consider what the merger does. It takes two objects that have been cooling for millions or billions of years, objects with relatively low entropy, and smashes them together. The collision dumps an enormous amount of thermal energy into the material. The shockwaves heat the interior. The turbulent mixing redistributes the heat throughout the body. The result is that the merged remnant has much higher entropy than a normal object of the same mass would have if it had simply formed from a collapsing cloud and cooled naturally. High entropy means the remnant is puffed up. It's larger and less dense than a naturally formed object of the same total mass would be. And a puffed up, high entropy object has lower core pressure and lower core temperature than a compact, low entropy object of identical mass. This is the cruel paradox. The merger gave the remnant enough mass to potentially become a star, but it also heated it up so much that the core conditions are initially farther from the fusion threshold than they would be in a freshly formed object of the same mass. Think of it this way. Imagine you're trying to light a campfire. You need the fuel to be compressed and concentrate to reach the ignition temperature. But someone has scattered the fuel across a wide area and heated it with a blowtorch that made everything expand outward. The fuel is there. The total amount of wood is sufficient, but it's spread out, puffed up, and in the wrong configuration. You have to wait for it to settle back together and concentrate before ignition can occur. That's essentially what the merged remnant has to do. It has to radiate away the excess thermal energy deposited by the merger, lower its entropy, and contract to the point where core conditions match what a naturally formed object of the same mass would achieve. And that process, the Kelvin-Helmholtz contraction we discussed, takes millions of years. There's another factor that complicates the picture. It's related to entropy but distinct from it. It's the question of degeneracy. As we discussed early in our story, brown dwarf interiors are partially degenerate. Electron degeneracy pressure, the quantum mechanical resistance to compression that arises from the Pauli exclusion principle, plays a significant role in supporting a brown dwarf against gravity. In a fully degenerate object like a white dwarf, the structure is almost entirely determined by degeneracy pressure and is nearly independent of temperature. You could heat a white dwarf dramatically and its size would barely change because degeneracy pressure, not thermal pressure, holds it up. Brown dwarfs sit in an intermediate regime. They're partially degenerate. Some of their internal support comes from degeneracy pressure, and some comes from ordinary thermal pressure. The relative contribution of each depends on the density, temperature, and mass. When the merger happens, the enormous injection of heat raises the temperature dramatically. This temporarily reduces the importance of degeneracy pressure because the thermal pressure becomes more dominant. The interior behaves more like an ordinary, non-degenerate gas. This allows the remnant to expand more than a fully degenerate object would, which is part of why it puffs up so dramatically. As the remnant cools and contracts over millions of years, the density rises and the temperature eventually starts to drop relative to the density. Degeneracy gradually reasserts itself. the interior becomes more degenerate again, and this creates a problem. A more degenerate interior resists compression more effectively. As degeneracy grows, it becomes harder for gravity to squeeze the core to higher densities and temperatures. The contraction slows. The march toward fusion conditions stalls. Whether the core reaches fusion temperature before degeneracy halts, the contraction depends on the mass. A more massive remnant has stronger gravity, which can overpower the degeneracy pressure and continue compressing the core. A less massive remnant has weaker gravity, and degeneracy may win the tug of war, stopping contraction before fusion temperatures are reached. This is exactly the same physics that sets the hydrogen burning minimum mass in the first place. The 75 Jupiter mass threshold exists precisely because it's the mass at which gravity can compress the core to fusion temperature despite the resistance of electron degeneracy. Below that mass, degeneracy wins and fusion never starts. Above it, gravity wins and fusion ignites. For the merged remnant, the situation is more nuanced than for a normally formed object. The thermal history matters. The merger heated the interior in a way that a normally collapsing cloud would not. The cooling and contraction path is different. The degree of degeneracy at each stage of contraction is different. This means the effective hydrogen burning threshold for a merger remnant might not be exactly 75 Jupiter masses. It might be slightly higher because the remnant has to radiate away extra entropy before it can contract enough. Detailed calculations and simulations suggest that the offset isn't enormous. A merger remnant might need a few extra Jupiter masses above the standard threshold to achieve sustained fusion, perhaps 78 or 80 Jupiter masses instead of 75. But that extra few Jupiter masses could be the difference between success and failure for remnants sitting right near the boundary. So what actually happens? Let's consider the different scenarios. Scenario 1. 2 relatively low-mass brown dwarfs merge. Say, 2 objects of 25 Jupiter masses each, giving a combined mass of 50 Jupiter masses. Even with no mass loss, this is far below the hydrogen burning threshold. The remnant will be a more massive brown dwarf. It will be hot and bright for a few million years as it radiates away the merger energy. Then it will settle down and resume the slow cooling that all brown dwarfs undergo. It will be indistinguishable from a naturally formed brown dwarf of the same mass after enough time passes, except perhaps for its unusually rapid rotation and possibly a remnant debris disk that fades over time. 2 failures combined, and the result is a bigger failure. Scenario 2. 2 massive brown dwarfs merge, each one between 50 and 65 Jupiter masses. The combined mass, even after accounting for mass loss, lands well above 80 Jupiter masses. This remnant has enough mass, enough gravitational squeeze to overcome the challenges of excess entropy and partial degeneracy. After millions of years of Kelvin-Helmholtz contraction, the core temperature reaches the fusion threshold. Hydrogen fusion ignites, the remnant stabilizes, it stops contracting, it reaches hydrostatic equilibrium with nuclear burning providing the energy to support itself against gravity indefinitely. This object is a star. A very small, very dim, very cool star, sitting at the extreme bottom of the main sequence. A red dwarf, the lowest mass category of true stars. It will be cooler and dimmer than Proxima Centauri, which is already one of the dimmest stars known. Its luminosity might be only a tiny fraction of the sun's output, less than 1,000th, perhaps less than a 10,000th. It would glow a deep, dark red. barely visible even through a powerful telescope from any significant distance. But it would be burning hydrogen. It would be sustaining itself. It would be a star. And it would potentially shine for an extraordinarily long time. The lowest mass hydrogen-burning stars are the longest-lived objects in the universe. Because they burn their fuel so slowly, they can persist for trillions of years, far longer than the current age of the universe. Our sun will exhaust its hydrogen fuel in roughly another 5 billion years. A star 10 times less massive could burn for 10 trillion years or more. That is more than 700 times the current age of the universe. A star born from a brown dwarf merger might still be shining long after every sun-like star in the galaxy has burned out and died. Long after the Milky Way has merged with Andromeda. Long after the cosmic expansion has carried most other galaxies beyond the observable horizon. In the far, unimaginably distant future, when the universe is cold and dark and nearly all other light sources have faded, this tiny star forged from the collision of two failures might be among the last objects still shining. Two objects that failed individually would have produced something that outlasts nearly everything else in the cosmos. That's a remarkable outcome. Scenario 3. The borderline case. Two brown dwarfs merge with a combined mass that lands right near the threshold. Say 76 to 80 Jupiter masses after mass loss. This is the most uncertain and most interesting scenario. Whether fusion ignites depends on all the subtle factors we've discussed. The metallicity, the entropy deposited by the merger, the degree of degeneracy, the rate of angular momentum loss, the efficiency of cooling. For some combinations of these parameters, the remnant manages to contract enough for fusion to begin, but just barely. The fusion rate might be extremely low, producing only a trickle of energy. The object might hover right at the boundary, technically burning hydrogen, but at such a low rate that it barely qualifies as a star. It would be dimmer than any naturally formed star, perched right on the edge between success and failure. What would such an object actually look like? Imagine a red dwarf so faint that it produces less light than a candle would if you could see it from a few miles away. Its surface temperature might be barely above 2000 degrees Fahrenheit, cooler than some of the hottest brown dwarfs when they're young. If you were standing on a hypothetical planet orbiting this object, your sun would appear as a dim, dark red disk hanging in the sky, providing so little light that the landscape around you would be perpetually in deep twilight. Not darkness exactly, but a permanent dusk. You'd see better by starlight on some nights on Earth than you'd see under the full glare of this tiny star at noon. An astronomer studying this object from afar would notice things that seemed off. Its luminosity would be strangely low for its mass. Its spectrum might show chemical signatures that don't quite match a normally formed red dwarf. Perhaps unusual ratios of elements left over from the merger process, or spectral lines broadened by the remnant's rapid rotation in ways that a typical, slow-spinning red dwarf wouldn't show. The object might still be spinning noticeably faster than other stars of similar mass, carrying the last remnants of the angular momentum that the merger deposited millions of years earlier. These subtle clues, a star that is too dim, spinning too fast, with slightly wrong chemistry, would be the forensic evidence that this particular star was not born the usual way. It was assembled from wreckage. For other combinations of parameters, the remnant falls just short. It contracts for millions of years, approaching the fusion threshold but never quite reaching it. Degeneracy pressure stiffens the core just enough to hold contraction, a whisker below the temperature needed for sustained fusion. The object becomes a very massive brown dwarf, hotter and more luminous than a typical brown dwarf of its mass because of its unusual thermal history, but ultimately not a star. A near miss, a failure by the thinnest possible margin. In these borderline cases, the answer to our question changes depending on details that are extremely difficult to predict. Small differences in the initial conditions of the binary, the exact masses, the exact composition, the exact orbital parameters can tip the outcome one way or the other. The boundary between stellar and substellar is not a clean wall. It's a fuzzy zone where outcomes are exquisitely sensitive to initial conditions. Let's also talk about what the rapid rotation does to the merged remnant's long-term evolution, because this is another factor that distinguishes a merger product from a normally formed object. As we discussed, the merged remnant inherits enormous angular momentum from the pre-merger binary. It spins fast, and that spin has real structural consequences. The centrifugal effects at the equator partially counteract gravity, reducing the effective gravitational compression. A rapidly spinning remnant doesn't contract as efficiently as a non-rotating one would. The core doesn't get squeezed as hard. Core temperatures and pressures are lower than they would be in a non-spinning object of the same mass. This means rapid rotation delays the onset of fusion, if fusion is going to happen at all. The remnant has to spin down significantly before contraction can proceed to the point where core conditions reach the fusion threshold. And spinning down takes time. Magnetic braking, coupling between the remnant and its debris disk, internal viscous processes, all of these gradually remove angular momentum, but they work slowly. The remnant might need millions of additional years of spin down before it can contract enough. In the worst case for fusion, rapid rotation might permanently prevent the core from reaching fusion conditions. If the remnant can't shed enough angular momentum, if the centrifugal support is too strong, the core might never get hot enough. The remnant would remain a rapidly spinning, massive brown dwarf, flattened into an oblate shape, forever unable to ignite despite having sufficient total mass. In practice, most models suggest that the remnant can shed enough angular momentum over millions of years for this not to be a permanent barrier. But it does slow down the timeline. A merged brown dwarf might take tens of millions of years longer to reach fusion conditions than a freshly formed object of the same mass would take. The star is delayed, not prevented. But the delay matters for observational astronomers trying to catch these objects in the act. Now, let's step back and distinguish the likely outcomes from the speculative extremes. Because when we're dealing with a topic like this, it's important to be clear about what the physics tells us with reasonable confidence versus what remains genuinely uncertain. The well-supported conclusion is this. If two brown dwarfs merge with a combined post-merger mass that is significantly above the hydrogen-burning threshold, perhaps 85 Jupiter masses or more, then the remnant will almost certainly become a star eventually. The excess entropy from the merger and the rapid rotation will delay the onset of fusion by millions of years compared to a normally formed object, but gravity will ultimately win. The remnant will contract, cool, and ignite. This outcome is robust across a wide range of models and assumptions. The genuinely uncertain region is narrow, roughly from 75 to 85 Jupiter masses of post-merger mass. In this zone, the outcome depends sensitively on the details. Small changes in metallicity, entropy, or angular momentum evolution can tip the result from star to brown dwarf, or vice versa. This is where the interesting physics lives, where the answer to our question becomes conditional rather than definitive. Below about 75 Jupiter masses of post-merger mass, the outcome is clear: no star. The remnant is a brown dwarf, albeit a massive one with an unusual thermal and rotational history. It will cool and fade like any other brown dwarf, just on a different timeline. It's also worth noting what this scenario does not produce. A brown dwarf merger does not produce a supernova. It does not create a neutron star or a black hole. It does not generate a gamma ray burst or any of the other extreme phenomena associated with the deaths of massive stars. These objects are simply too low in mass for any of those outcomes. The most dramatic possible result, and it's dramatic enough, is the birth of a new star from objects that individually could never have become one. We should also acknowledge something important about the current state of our knowledge. No one has unambiguously observed a brown dwarf merger in progress. These events are rare and faint. They happen in the darkness between stars, involving objects that are already dim and hard to detect. The theoretical framework for understanding them is well developed, built on established physics of tidal interactions, hydrodynamics, stellar structure, and nuclear physics. Computer simulations have explored many scenarios, but direct observational confirmation remains elusive. There are some candidate objects that might be merger products. Unusually luminous brown dwarfs, or brown dwarfs with anomalous rotation rates, or very low mass stars with properties that don't quite match normal formation models. These objects hint that mergers might have occurred, but the evidence is circumstantial, not definitive. But this might be changing. The James Webb Space Telescope, the most powerful infrared observatory ever launched, is giving astronomers an unprecedented ability to study the faintest and coolest objects in the galaxy. Its infrared sensitivity is exactly what's needed to detect the telltale signatures of brown dwarf merger remnants. What would those signatures look like? A few things stand out. First, the debris disk. A recently merged brown dwarf should still be surrounded by a disk of warm gas and dust expelled during the collision. This disk would emit infrared radiation that the Webb telescope could detect. Finding a massive brown dwarf or very low mass star surrounded by a disk that's too warm and too close to be a normal planet-forming disk would be a strong hint that a merger occurred. Second, the unusual luminosity. A recently merged remnant should be brighter than a normal brown dwarf of the same mass because it's still radiating away the excess thermal energy from the collision. If astronomers can independently measure the mass and the luminosity of the same object, and find that it's significantly overluminous for its mass, that discrepancy points toward a violent thermal history like a merger. Third, rapid rotation. A merger product should be spinning much faster than a brown dwarf of the same age that formed through normal collapse. Spectral line broadening caused by rapid rotation is measurable, and finding a brown dwarf or low-mass star that's spinning far faster than its peers would be another piece of the puzzle. None of these signatures alone would be conclusive. A disk could have other explanations. Overluminosity could reflect a young age. Fast rotation could be a coincidence. But finding all three together in the same object, a rapidly spinning, overluminous disk-bearing brown dwarf or borderline star, would make an extremely compelling case that we're looking at the aftermath of a merger. Future surveys with the Webb telescope and the next generation of ground-based, extremely large telescopes may finally provide the direct evidence that has so far eluded us. So let's bring this all together. Let's answer the question we start with. Can two failed stars combine to make a real star? The answer is yes. Conditionally, provisionally, but genuinely yes. If two brown dwarfs are individually close enough in mass to the hydrogen burning threshold, if their combined mass after accounting for merger losses is safely above that threshold, then the merged remnant can contract over millions of years and ignite sustained hydrogen fusion. Two objects that each individually fail to become stars can, together, succeed. The merged remnant becomes a very low-mass red dwarf, the smallest and dimmest kind of star, but a star nonetheless. An object that generates its own energy through nuclear fusion and can shine for trillions of years. But this outcome is not guaranteed. It depends on the specific masses of the two progenitors, on how much material is lost during the merger, on the chemical composition, on how much thermal energy the collision deposits in the interior, on the degree of electron degeneracy in the core, on how quickly the remnant can shed its enormous angular momentum. If any of these factors conspire against ignition, the remnant will remain a brown dwarf, a more massive, hotter, faster spinning brown dwarf than either of its parents, but still a brown dwarf. Still substellar, still fading. The universe doesn't give participation trophies. You either cross the threshold or you don't. And for objects sitting right on the boundary, the margin between stellar and substellar can be excruciatingly thin. A few Jupiter masses, more or less. A slightly different composition. A slightly more or less violent merger. These small differences determine whether the remnant shines for trillions of years or fades into cold darkness. There is something deeply poetic about this whole scenario. Two objects born from the same collapsing cloud, each one falling just short of the mass needed to sustain fusion. Each one destined to cool and darken over billions of years. Alone, each one is a failure, a dim, fading ember that never quite caught fire. But together, locked in a gravitational embrace that slowly draws them closer over eons, they can transcend their individual limitations. The collision reshapes them. The merger combines their mass, and from the wreckage of two failed stars, a real star can be born. Small and dim, barely a star at all, but burning, fusing hydrogen, generating its own light in the darkness. It's as if the universe provides a second chance, a way for objects that individually fell short to collectively succeed. Not always, not easily, not without a specific set of conditions aligning just right, but sometimes, under the right circumstances, two failures can add up to one success. And if that newly born star happens to have planets forming from the debris disk expelled during the merger, if those planets settle into stable orbits around this tiny red dwarf that was forged from the collision of two failed stars, then somewhere in the galaxy, there might be a world warmed by a sun that almost never existed. A sun that was, in a very real sense, born from failure. The universe is full of stories like this. Objects and processes that seem straightforward on the surface, but reveal extraordinary complexity when you look closely. Brown dwarfs are not just failed stars. They're objects with rich, complex physics, capable of participating in events that can change their fundamental nature. The boundary between star and not star is not a wall. It's a landscape, full of subtlety and nuance, where the outcome depends on details that are easy to overlook, but impossible to ignore. The next time you look up at the night sky and see the faint glow of a dim red star, barely visible to the naked eye, consider the possibility that it might not have been born the usual way. It might be a merger product, an object forged from the collision of two brown dwarfs that spent billions of years spiraling toward each other in the dark. Two failures that became, through violence and patience and the relentless mathematics of gravity, one quiet success. Somewhere out there, in the vast spaces between brighter stars, this might be happening right now. Two brown dwarfs, locked together, spiraling inward, approaching the moment when they'll merge and face the question that defines their existence. Can we become a star? And sometimes the answer is yes.